So today we will start with lecture 5, and in this lecture 5 I am going to review the topics covered in the first 4 lectures, and this essentially forms chapter 1 of my book. Now what we have seen in the first 4 lectures is that many engineering design problems can be converted to optimization problems. And this is one of the main reasons for the importance of optimization as far as engineering and science domains are concerned. And this also percolates into fields such as business management, where many problems such as profit maximization and so on can be converted into optimization problem. Now, it was important to form a certain standard form of the optimization problem so that different people can essentially use the same mathematical structure for this problem. And we developed the standard form of this problem where we essentially minimize the function subject to certain constraints such as h of x equal to 0 and g of x is less than equal to 0. We also saw that the key elements of the optimization problem included objective functions and constraints, design variables, and optimal values. Now typically you have one objective function, but you may have more than one objective function, in which case it is a multi-objective optimization problem. Now regarding constraints, we saw that there are two basic types of constraints: the equality constraints, which we use the nomenclature h of x equal to 0, and the inequality constraints where we use the nomenclature g of x is less than equal to 0. And we saw that there is a certain space or a set of points called the feasible region where the design variables are such that the constraints are satisfied. Now in many cases in typical design, it's actually the feasible region which you are looking for. So if you are looking for a structural optimization problem with constraints on frequencies, buckling, failure criteria, and so on, then essentially you want the dimensions of the structure such that it does not fail. And therefore all the possible designs which do not fail are part of the feasible region. So essentially we can say that classical design would require you to formulate a problem with a proper set of constraints and the objective functions, and then to ensure that you are in the feasible region. So in many cases in practical problems, it's actually quite difficult to come up with points which are in the feasible region. Now, any part of the design space which is not feasible is called the infeasible region. And here again, there are some issues which we will encounter later, is that there may be situations in physical problems where if you get into the infeasible region, then your simulation or mathematical model may not converge. So this is often the case in certain type of nonlinear problems. Now, if the objective and constraints are linear functions of the design variable, then you have a linear programming problem. And if one of the objective or the constraints are nonlinear functions, then you have a nonlinear programming problem. Similarly, you have unconstrained and constrained optimization problems. And problems where you have no constraints are essentially where you have unconstrained optimization problems. If you have even one constraint on the problem, you have a constrained optimization problem. Later we will see that there are certain methods known as penalty methods by which you can convert constrained optimization problems into unconstrained optimization problems, which are typically simpler to solve. Now, the optimization problems can typically be solved using direct methods or indirect methods. Now, direct methods typically search the design space for the optimal point, and these are essentially numerical methods where you may start with one point or with a population of points, and you essentially move around the design space, sometimes through the feasible region. In some cases, you may even go to the infeasible region, and essentially your aim is to then come back into the feasible region and then get the optimal point. So most of the methods in optimization are essentially direct methods. However, we have seen in this first chapter the use of the indirect methods, which essentially use some kind of optimality criteria to find the optimal point. And the optimality criteria essentially means necessary and sufficient conditions. So we saw that the necessary conditions and the sufficient conditions for a point to be a minimum point need to be found. And in the case of an unconstrained optimization problem, using the Taylor series expansion and the first term of the Taylor series expansion in terms of the first derivative, we found that the necessary condition was that the first derivative of the function with respect to the design variable becomes 0. Now, if you have a multivariate function, the gradient vector for this multivariate function has to be set equal to 0. So this is a very fundamental theorem in optimization, which you can use for a plethora of different type of functions and problems. Now, of course, the important point here is that the gradient vector must be something which you can calculate. So the function must be differentiable. So again, that is a problem which sometimes you may face, is that you may have a function which is not easy to differentiate or which you cannot differentiate, and in those cases you may need to resort to methods which do not use the derivative of the function. So essentially these may be functions for which you can only calculate the value of the function, that is f of x, and not f dash of x. So again, we will sometime discuss some of those methods which are also known as gradient free methods. Now, this criteria that the first derivative of the function should be set to 0, or the gradient of the function should be set to 0, leads to a point known as a stationary point. And the stationary point is essentially a point which could be a minimum point, could be a maximum point, or it could be a saddle point. Now, of course, if we are looking for a minimum point, we don't want to find a maximum point, because that would defeat the basic aim of doing the whole optimization problem. If you are doing a weight minimization problem for an aircraft structure, you don't want to land up with a weight maximization problem. That's not something which your company or institute is going to like. So one of the things you need to do is you need to calculate the second derivative of the function with respect to the design variable. And if this is positive, then the stationary point is a minimum point. And again, this concept is extended to multidimensional space, where the Hessian matrix must be positive definite for multivariate functions. So again, here you can see that this whole concept comes from calculus, and therefore it requires the function to be differentiable at these points. So again, if you have functions which are not good in terms of having derivatives, then some of these methods have problems. And so we then look at gradient free methods. Now, typically what happens in optimization is that for many functions, it is not easy to calculate the Hessian matrix, because it involves a huge amount of derivative calculations, and in many situations you may need to calculate these derivatives using finite difference approximation. And therefore, a practical way to see if you have a minimum point is to look at your starting or baseline design and then compare it with the stationary point design you have obtained. And if you have obtained a sufficient reduction in that design, then most engineers are quite happy that they have obtained a minimum point. So this is a practical type of situation. But in the case you are able to calculate the second derivative, then you of course can do it and verify that particular issue. Now, when you turn to constrained optimization problems, we saw that we can create a Lagrangian, which essentially is a composite function which includes the function and the constraints. And as far as the constraints are concerned, you add or multiply these constraints with Lagrange multipliers. And as far as the gx less than equal to 0 type of constraints are concerned, you add certain variables which are positive numbers, which are known as slack variables. And therefore you can then create this Lagrangian function. Now you create a KKT condition which results from the minimization of the Lagrangian and yields the candidate minimum point. So this is the Karush-Kuhn-Tucker condition, which is very important as far as optimization is concerned. So essentially you take the derivative of the Lagrangian with respect to the design variable, with respect to the Lagrange multipliers, the slack variables, and all the different variables you have introduced into the problem, and then you set these equal to 0. Now, we also saw that there is a particular peculiar case where if the function and the constraints are convex functions, then the point is also a global minimum point. So in which case the local minimum predicted by the KKT condition also becomes the global minimum point. So again, this is something which you can show in certain cases, but in some different cases, if you are not able to show this, you can always look at the point which you have obtained from this KKT condition and compare it with the typical classical design based on conventional methods and see if this becomes a better point than the point you started with. So the basic premise of this entire course is that many engineering problems and also problems in the real world in general, I can extrapolate it more generally, can be posed as optimization problems. And for simple problems, you can often get explicit functional expressions for the objective functions and constraints. And this is also sometimes possible if you resort to certain methods known as surrogate methods, where you create approximations of a complex problem in terms of simple polynomial functions, and then you use those for solving the optimization problem. So this is sometimes known as response surface methods, which we will discuss later in this book. But for most practical problems, the objective and constraints are connected to the design variable through a computer program. That will be the focus of some of our next few chapters. And this happens because a plethora of the engineering problems as well as general design problems have been computerized. And essentially the governing equations which are used to solve this problem can be solved in a simple manner by using the computer. And therefore, if you are looking for any such objective or constraint, suppose the objective function is to reduce vibration of a structure and your constraints are on buckling or flutter or frequencies, then you will typically have a code or a software which will calculate these for you. And therefore, you then do not have the simple function there in the fx, hx, and gx form which we have considered in this chapter, but these will be coming from essentially black box computer programs, and then you need to work with these particular computer programs. So one of the ways to do this is to use the direct method, which essentially move around in the design space and try to find a minimum point. In the process, they may not actually find a minimum point, but they may certainly find a point which is much better than your starting design, and therefore the use of optimization will probably produce a design which is much better than what was produced in the conventional engineering problem. And this kind of approach becomes very important because nowadays the engineering people want to extract more and more out of the design process. So for example, if you are doing an aircraft design problem and you have to bring down the fuel consumption, in that case, even a small improvement in terms of fuel consumption may translate to millions of dollars saved during the flight time of the particular flight vehicle. Therefore, optimization can be very important, and you will see people spending a lot of advanced optimization time and money in designing things such as the tip of the wing or the various material combinations which are used and so on. And these essentially bring down the weight of the particular vehicle, the vibration of the vehicle, and many of these factors. And when this vehicle is then produced in large numbers, such as in thousands or millions, the net effect on the entire system is very substantial, because essentially you have thousands of planes flying around which are consuming less fuel, and therefore the fuel consumption of the entire company or the sector at large becomes less, and that can have so many positive consequences in terms of the profitability of the company or in terms of reduction of global warming and so on. So this was A basic background on optimization we have covered in the chapter 1, and this is some of the basics which you need to know. And in the next chapter we are going to start talking about the direct methods, which are more suitable when you have computer programs which generate your objective function and constraint. So that is the end of lecture 5, and I will see you in my next video in chapter 2, which begins lecture 6. Thank you very much.